and maybe we'll talk about this more on Wednesday night or something. But it's very nice. My talk, well, we've all been hearing about Sammy, and we all know about his contributions to algebraic topology and to category theory. But there's another part of him also, namely he wrote 2 thick volumes on finite automata theory and computability. He was going to write 4 thick volumes, but he wrote 2 of them. The green things. So, in some sense, this is, of course, it has nothing to do with what he was doing, but just something about computation also I want to contribute. Okay, so, in order to tell you about algorithmic information content, I got to tell you what classical, what it is classically, what classical algorithmic information content is of strings. And so that's called Kolmogorov complexity, and we'll talk about that. And that's based on what's called the Turing machine, which is a standard way of discussing computation. But we don't want to talk about strings, we want to talk about categories and functors and natural transformations. So we're going to need another programming language. Okay, and then we'll bring these two ideas together and talk about Kolmogorov complexity of categories, or categorical structures. We'll talk about some complexity theory, about categorical structures, and computability theory about categorical structures. Okay, and then we'll go on as time gives us. So this is classical motivation. What's Kolmogorov complexity all about? So consider these 3 strings. Notice they're all the same length. They could be flipping a coin and getting zeros, heads or tails, zeros or ones. They could be like that. However, if you look at it, the first one is just 45 zeros straight off. Okay? The second one, if you look at it, is 2 ones, 3 ones, 5 ones, 7 ones, 11 ones, etc., prime numbers, separated by zeros. And the third one was just me hitting the zeros and ones in a semi-random way. Okay? So that's that. Now, in some sense, the first string is much simpler. It has less algorithmic information in the second string, and the second string has less algorithmic in the third. Now, the way to quantify this, the way to somehow put a measure of what these things are, is to write a computer program that prints out these strings. And here's 3 different programs. Okay, print 45 zeros. I'm being vague here because I don't want to talk about Turing machines. Print the first 6 primes. Obviously, you have to write with zeros and in monomial and put the 0 in between them. And the last one is random. Okay, and the only way to do that is just say print the string. Okay, so there's an interesting concept here. You have simple strings have simple programs, then you have more complicated programs, more complicated, more complicated, more complicated. Finally, you reach random. We usually don't think of random as the limit of complicated, but in a sense that's the way it is. Okay, now to be a little bit more formal about this, you got to talk about Turing machines. You got to talk about some type of Turing machine. So let U be a universal Turing machine. And if you don't know what that is, then don't worry about that. K of S, K of the string, Kolmogorov complexity of the string, is the minimum length of P. P is some program. And you can have U of P, the universal programming of the program P. And you can have nothing on the tape. Lambda is empty on the tape. Okay, is equal to S. So you want to go through all Turing machines and find the smallest such one. Okay, there's also something called relative Kolmogorov complexity, which we're going to use something similar. If you're given T, if you have on your Turing machine tape, you're given T, and you want to get out S, how do you do that? And again, it's the minimum program. So again, if K of S is greater than the length of S, that's the third case, where the only way to print it out is if it's just like print, then it's incompressible. The idea is if you have a short program, then you can compress it to the short program. Okay, so we have these ideas going on. Compressible, algorithmic information. Okay, another word for incompressible is random. Okay. Okay, now that's great. But I don't want to talk about Turing machines, and I don't want to talk about strings. I want to talk about categories, functors, and natural transformations. So I want to invent a programming language that can discuss these different structures. Okay? And I want to formulate a programming language that can I want to write a programming language that can formulate these different structures, and then talk about what's a complicated structure, what's an uncomplicated structure, what's a random structure. Okay? And so I did this. Okay, and now I did this, I started working on this like a year before I knew about this conference, and I called the programming language Sammy, after Sammy Eilenberg. So, but that's whatever. It's just a joke. But again, keeping in mind that he had something to do, and I needed a flashy name, so I got it. Okay, so what does this programming language have? It has constant categories, the empty category, the category with one object, the category with two objects, and an arrow in between, and also the category of cat. And again, what we're going to try to do is, we're going to try to describe categories using these things. Okay? There's going to be constant functors from 1 to 2, the source and the target. Okay, that takes 1 to 2. And then there's going to be operations that this programming language is going to have. Now, if you're worried about how you're going to implement this programming language, don't. And I'll tell you why later, because it can't be implemented. Okay? If C is equal to the source of F, the functor from A to B, then you're going to have the source of C is the source of that functor is going to be A, the target of the functor is going to be B. These are the trivial type of operations relating categories to functors and things like that. If you're going to have the identity on A, so then you can, given the category A, you can get the identity on A. These are trivial little categories, operations. A slightly more complicated operation is horizontal composition and vertical composition, to be thought of as natural transformations. So you can take two composable natural transformations, composable this way, composable that way, and you get that. I'm sorry, I skipped the operation. Okay, and then you can take A to the B. Take two categories, from two categories between them. Okay, now basically this programming language is going to be a sequence of equal steps. You're also going to be able to compare two things. You can say if this natural transformation is equal to that natural transformation, then go to that label. You'll be able to have loops and stuff like that. Okay, and once you get into loops, you can ask yourself the question, will the program stop, and things like that. Okay, but let's just go on with the operations. We have four more operations, namely con extensions. Okay, if you have two functors f and g, then you can take the right con extension. And since you have the op operation, you also get the left con extension, so that's fine. Okay, and then there's another operation, namely con induce. In other words, con extensions, you get something induced by that. And so if you have something that's built up with f and g, the con extension is built up with f and g, and then you have another h and theta, then you can get that. And the idea to keep in mind is an example of a con extension is a product. Okay, and if you have a product, this is the product of these two things, and if you have something else, then this is the induced functor. Left con extensions are made by the op operation, so we talk about right, we talk about left. Okay, using con extensions, one can derive products, co-products, push-outs, pullbacks, equalizers, co-equalizers, constructible limits, co-limits, ends, co-ends. As McLean says, all concepts are con extensions. Okay, but then there's something else. If G is from A to B is a right adjoint, the left adjoint, and then its left adjoint, can be found as a con extension. So you get right adjoints, quasi-inverses, inverses, they all come as con extensions. Okay? There's another thing, and sorry, well, I don't want to write it because I don't want to write it. Con liftings. Con extensions are when you have two things going this way. What about if you have two things going that way? You have con liftings. We need those also. Okay, so these, and of course, what's induced by them. A few more other operations, but nothing serious. The obvious thing is, the most important thing is the con extension, because you get all the limits and the co-limits and things like that. So basically, you have composition and con extensions. Okay. A few remarks about SAMI. First of all, this is not the first programming language for categories. Ridehead and Burstel, they have a programming language, and this Hagiano's thesis has a thing. There's a slightly difference between my work and their work, namely they're trying to implement it. I have no interest in implementing it, and you'll see why. Also, it's not necessarily the best programming language, not necessarily the smallest programming language. Very simple. If you have target, if you have source and op, you automatically can get target. So you don't need you can cut your programming language much shorter. But I'm not interested in, I want something readable. Okay? You can also only talk about natural transformations, but that's not going to make you a very readable thing. But again, we'll talk about if you don't like my programming language and you want to make another one, that's fine. I'll show you why. Notice that in this programming language, numbers, strings, trees, graphs, arrays, and other data types are not mentioned in SAMI. I didn't talk about that. I just talked about categories and these small operations. They can be derived, and we'll see. We're going to spend a lot of time talking about numbers, even though it's not mentioned in the programming language. Categories and algorithms are more primitive than numbers, strings, etc., etc. So we're going to keep it. That's a little bit of a philosophical statement. Okay. Next, we're in need of some kind of Church-Turing thesis. Let me say, classically, the Church-Turing thesis says that whatever is computable by a Turing machine, whatever a Turing machine is. I like to say as follows: whatever can be done can be formulated in categories can be formulated by this SAMI programming language. Okay? Now, it's a thesis. It's not a theorem because it's hard to prove, because I can't tell you exactly what can and cannot be done formulated by categories. So we have that same problem. Okay? If you know classical Kolmogorov complexity, there's a whole discussion about self-delimiting. We don't have that problem. Next, these programs that we're going to have, they're going to be finite sequences with labels, and you're going to be able to jump back and forth, etc., etc. But they're finite things. They can be encoded and decoded. In other words, I can make a number for every SAMI program. More important, I can make a functor from the trivial category to the natural number that describes some SAMI program. We get self-reference. Okay, you have a functor talking about a category which could describe the functor. So you get this self-reference and you get all types of interesting logical things. Okay, so now let's go through some basic definitions. K of SAMI, Kolmogorov complexity of SAMI, obviously I'm going to leave out that SAMI, is the smallest number of operations needed to describe C, a category. But I don't only want to do it for a category, I want to do it for a functor, for a natural transformation. I also want to do it for, let's say, a monad, or a comonad, which is a bunch of categorical structures. I want to know how many operations do I need to describe a monad or a comonad or some type of other structure. Okay? Now, in classical Kolmogorov complexity, you have something called the invariance theorem. The invariance theorem is like this. Let's say you don't like my universal Turing machine that does it. You have another universal Turing machine. Well, they can describe each other, so we leave it alone. So, same thing here. Let's say you don't like SAMI and you want to make your own programming language. We'll call it Saunders for the other creator categories. Okay? Well, it doesn't matter, because if both of our programming languages are expressive enough, they should be able to describe each other's things, and so we should be able to make, what is it called? When you change one program from one programming language to another programming language, emulate? Say again? Emulate? Emulator. Okay, so we should have that. Okay. Now here's a typical type of theorem that you're going to find of this type. Namely, let's talk about left-con extensions. Okay? Left-con extension consists of a functor and a natural transformation, and so you say as follows. The Kolmogorov complexity of a left-con extension and its natural transformation is less than or equal to, how am I going to describe that? It's either going to be the Kolmogorov complexity of the functor, F, plus the Kolmogorov complexity of the functor G. But one second, while building G, I already have F. So I take off a little bit of information. I might use, in constructing G, I might use part of F, or some things that are constructed from F, so I might use that information. And then, given these two functors, you do one or two operations, some constant operations, and you get the left-con extension. So those are the type of theorems you're going to get, that these things depend on each other. But that's somewhat trivial. Okay, now here's one of the main terms. If A and B are two equivalent categories, then K SAMI of A is up to a constant equal to K SAMI of B. In other words, that's a shocking theorem. What it says is as follows, is you can construct a category in one very complicated way, and you can construct a category in a very uncomplicated way, but if those two categories are equivalent categories, then it's actually the smallest way to do it. And the conclusion is that Kolmogorov complexity is an invariant of categorical structures. So that's nice. Up to a constant, so that's why it's a wiggly equal sign. But again, the constant's given beforehand. There is a constant such that if you give me any two categories. And the idea is, let me just say the idea. There's two ideas. One is that if you have an equivalent category, you can build one from the other in some sense. If you have an equivalence, you can build one from the other. And the other idea is that Sammy cannot distinguish identical elements, okay, which is the way it should be in category. I'm saying Sammy cannot distinguish isomorphic elements, which is the way it should be.
The programming language cannot see the axiom.
Say it.
How will your programming language simulate the axiom choice?
I don't know. I want to ask you a question. In cat, does the axiom of choice exist or not? It depends. If you want it to exist or you don't want it to exist. So I don't know. And so I don't know how you, like I said, it's not implementable, so I don't have to make a decision. Okay, so let's go on. Let's talk about some computing with these things. Take the co-equalizer of those two categories. Again, one is the trivial one-element category, two is the arrow. Okay? And take the co-equalizer of the source and target that takes this arrow and bends it around. That gives you the monoid of natural numbers. Okay? Take the arrow, so that's by the way, that's just interesting in itself. You have a finite category, you take a co-equalizer, you get an infinite category. Okay, which goes to show you that somehow this is not very implementable. Okay? Take the arrow category of this gives you the totally ordered category like that. Okay? And a functor from 1 to the natural numbers is just simply a number. So we're going to talk about that. Okay. A theorem. Any partially computable function of natural numbers can be computed with Sammy. I shouldn't have written the word partially. It has to be total, because it doesn't make sense. In other words, if the functors... Okay, anyways. So just with these natural numbers, describing natural numbers like that, you can describe any computable function, total computable function. Okay, but another way of dealing with this, so the way that theorem is done is with recursion and composition and new recursion and things like that. But another way of talking about it is the Turing machine. So let's talk about Turing machines. Think of the natural numbers as a totally ordered category, 0, 1, 2, 3. But I want to think of it as an infinite tape of a Turing machine. Now, P from 1 to n is not a number, it's the position that the head of the Turing machine is looking at. Okay, so you have this Turing machine and you're looking at different parts and you're moving to the left and to the right. Now look at this 3 hat. 3 hat is it's this category with 3 objects and isomorphism in between them. I want to think of this as the alphabet. Namely, the alphabet of 0, 1, and blank. Now consider a functor from the natural numbers, the tape, to 3, the alphabet. That assigns every position of the tape, it assigns it a letter of the alphabet. Okay? And that's basically a string. That's going to fill up your string on your tape. Okay. Theorem. Okay, so now what we have to do is, and I'll show you on the next slide, we have to manipulate these functors from the natural numbers to 3. Okay, manipulate them, change them around. And that's exactly what Turing machines do. And we do that. But conclusion, K classical, in other words, the Kolmogorov complexity for the classical, how many Turing machine operations do you have to create this string, is up to a multiple constant, and you'll see why, K Sammy of f of the string. In other words, think of the string like this, then you have it's up to same. Conclusion, our Kolmogorov complexity is a generalization of classical Kolmogorov complexity. In other words, because we did that. Now, it's a little bit painful to actually manipulate functors. Think about this. You have a functor from one category to another category, and you want to change its value in one place. How do you do that? It's painful. Anyways, but it's not so painful if your original category is this straight line category. So basically what you do is you take the category, you take the tape, the Turing machine tape, you bust it into two, okay, and then you put in the new value right over here. You put in the new value, you take the old value, and you can change the Turing machine tape. Okay? Now that's a bunch of operations in SAMI. Conclusion, for every single Turing machine operation, you can do a bunch of SAMI operations and do the same thing. Okay. Now, question, what's the power of categories? What does categories do? Okay. Now I told you, Turing machines, SAMI can do any total computable function, including this Holt prime. Let me tell you what Holt is. Holt is a classical thing that a computer can't do. It cannot tell when a machine, given a machine and an input, whether it's in an infinite loop or not. Okay? Holt prime is something different. Given a program program Y, input X, and time T, tell me yes or no, will the program stop? Okay, again, I cannot tell you, a computer cannot tell you if a program is in an infinite loop. But it could tell you if a program is in an infinite loop, or if a program is still going after 10 minutes. Here's the way you do it. Run it for 10 minutes, see if it's still going, then it's... So that's decided. Okay? It's decidable by a Turing machine, and it's also decidable by us, by SAMI. Okay? Now, take that Holt prime, which takes 3 inputs, take the projection of the natural numbers across the natural onto the natural numbers. In other words, forget T, and you get the Holt program. So I can formulate the Holt functor. Okay, so again, a regular Turing machine cannot solve the Halting problem, but SAMI can. Okay? And it's not so counterintuitive. Essentially, what this proof says is Holt of x, y is the co-limit of Holt prime of x. In other words, look towards the end and see what it is. The idea is, it's not so shocking because categories can do infinitary operations. You have infinitary limits and co-limits, so you can do an infinitary operation. It's not a problem. SAMI can solve the Halting problems. Kolmogorov complexity is a proper generalization of possible. So, in other words, SAMI can do more. Okay, can SAMI solve everything? I'm not saying what everything is. And the answer is no. I'll tell you what it can't do. The functor K of SAMI, which takes categorical structures and gives you the number of operations, okay, is not constructible with any SAMI program. In other words, and this is something from classical Kolmogorov complexity. You have Kolmogorov complexity, you have books this thick, and the point is, you can't calculate what the Kolmogorov complexity of a string is. Okay, so too, you can't calculate what the Kolmogorov complexity of a categorical construction. The proof is a categorical version of the regular one. Okay, so what exactly is the power of categorical constructions? I don't know, but I think, conjecture, I think it goes through the arithmetic hierarchy. And I just think that talking descriptive set theory in Warsaw is just the right thing to do. So it goes through the arithmetic hierarchy, and I think it's into the projective hierarchy. But again, I'm working on it. I'm not sure. Okay. Let's talk a little bit about algebraic structures. So you have an algebraic theory, Levere algebraic theory, and you have the category of algebras for that. Well, here's the idea. Given a category of, given an algebraic theory, you can construct the category of algebras. And for an algebraic theory, you can go back and reconstruct the theory also. Okay, so you go both ways. Conclusion, those two things are basically the same. They have the same Kolmogorov, they have the same information content. Okay? More important, if T is Morito equivalent to T prime, in other words, if that category of algebras are the same, then they have the same thing. Now, you've seen this. There's the usual definition of, let's say, the theory of groups has 3 operations and three axioms. But there are definitions of the category of the theory of groups with 1 operation and this very, very long axiom. Okay? So again, that's basically, it's saying the same thing, namely, it doesn't matter, the Kolmogorov complexity of the theory is what's important. Not anything else. Okay, same thing works with monads, and so we'll leave it with that. And Kolmogorov complexity is an invariant of algebraic structure. Okay. So we have 5 more minutes. I just want to go through some future directions, some 5 little ideas that I'm working on, or I'm in the middle of, to show you why this is interesting. Okay, first of all, generalizations. Okay, nobody talks about categories of functors anymore. We talk about categories with limits, monoid categories, enriched categories, quasi-categories, infinity end categories, categories with equivalent model structure, categories with factorization system, all these types of things. And again, it's interesting to see how these things go. By the way, for equivalent model structure, what has more information, what has less information? The original category, the category, or the homotopy category? And the answer is, you have to describe what the weak equivalences are in order to get the homotopy category. So it's going to have more information. It'll be higher. Okay, next. In classical Kolmogorov complexity, there's a relationship with entropy. So you have Kolmogorov complexity is one thing, and Shannon's entropy is another thing. Shannon's entropy is basically how much you can mix up the structure, the strings. Okay, and there's a nice theorem that relates these two. Basically, Shannon's entropy is the average Kolmogorov complexity. Again, they're measuring 2 different things. Kolmogorov complexity measures the structure of a string. Shannon's entropy measures the information of a source of string, communicating a whole source of string. But it's basically that. What I would like to do is talk about the entropy of a category or of a natural or a functor. And the idea is as follows: how rigid is your definition? If you have defined a category, how rigid is your definition? How much can you move things around? Okay. And there should be some type of similar type of theorem. Okay. Gödel's incompleteness theorem has a Kolmogorov complexity version, which I think is very interesting. Okay? Consider a universal Turing machine. Actually, I think it's the right proof of Gödel's incompleteness theorem. Gödel's incompleteness theorem says there exists a statement that's true but unprovable. This is more powerful. This says there are many, many statements that are true but unprovable. Okay? Consider a universal Turing machine U and a consistent, sound, finitely specified theory T, strong enough to formalize arithmetic. So basically, we're talking about the same thing as Gödel's piano arithmetic or whatever. There exists a constant C, which is based on U and T, such that for all but a finite number of x, the statement K of x is more than n, where n is greater than that, will be true but unprovable. So here's a way of getting a whole bunch of statements that are true and unprovable. Okay? This is basically from Gregory Chaikin and Kalud. And the theorem essentially says that a logical theory cannot prove a theorem that is more powerful than the theory itself. Okay? And sometimes said as follows: a 50-pound logical system cannot prove a 75-pound theorem. So there's like a structure there. You have a set of statements that it can prove, and then there's the outside which it cannot. Okay, we want to understand the categorical structures and how much of a phenomenon they can hold. And you'll see this later on when I talk about, in 2 slides, when I talk about Occam's razor. Let's talk about this. Special relativity. Okay? One of the central aspects of quantum information theory is the notion of entanglement. Okay, so entanglement is as follows. If this is spinning, and if take 2 particles that are bound together, send one to Alpha Centauri, send one to keep one on Earth. If you measure this one, and it's measured down, spinning down, then you automatically know that that one is spinning up. Okay? And you know it instantaneously across the universe. Okay? Now, the whole idea is it's in a superposition beforehand. You didn't know it beforehand, and yet you get instantaneous information. Now, physicists tell you there's a problem with this because special relativity says you can't transmit information instantaneously. Okay? Physicists tell you, no, don't worry about that because that's not the type of information we were talking about. Okay? But they don't really say what type of information they restrict and what type of information they're not restricting. And they say some words like causality, but it doesn't make sense. But I think we can get to this if we talk about the mathematical structures that are holding these types of information. Okay. Occam's razor is usually seen as a criterion instead of a utopia. Occam's razor is usually seen as a criterion by which to judge different physical theories. Basically, what physicists do is they define functors from physical phenomena to mathematical structures. Okay, they have a lot of different physical phenomena that have mathematical structure, and they want to relate the physical phenomena to a mathematical structure. Again, the physical phenomenon is not really a category, but we'll make it as it is. Okay, universality of the theory demands that the category of physical phenomenon be as large as possible. Okay, so that was the main thing of Newton. You know, he said terrestrial and extraterrestrial phenomena are all the same. So that's universality. Occam's razor demands that mathematical structure has a low informational content. So this is what we want. We want to talk about what is the informational content, how much information can a certain mathematical structure hold. Okay, and this is getting back again to that stuff about Gödel's incompleteness theorem. You know, that a 50-pound mathematical structure can hold a 75-pound phenomenon. Okay, we are interested in using Kolmogorov complexity on both of these categories and the functor to better understand why does Occam's razor work so well. Not that it works, I'm not sure it works all the time, and people argue about that, but it seems to work well. Jim Crude. I misspelled it last time, but anyways, any questions?
Thanks a lot for the interesting lecture. Are there questions?
So you do not have implementation, but you have at least mathematics.
By the very fact that Turing machines, that semi can solve the Halting problem, means I can't implement it on a computer.
Let's see whether a semi exists. So operations are what? It's your operation.
Operations are ways of getting from one categorical structure to another.
Are these functions?
Right.
So you can put your functions at least in some axiomatic set.
Right. And essentially, this is Lever's paper on. I mean, Lever didn't talk about, but this is Lever's paper on category of categories as a foundation of mathematics. He gives a set of axioms. He doesn't talk about limits and co-limits, but essentially that's the con extensions are basically that.
Any questions? Yes, please.
I have a question about your invariance theorem. So you said that equivalent categories have the same complexity.
Equivalent categories have the same Kolmogorov.
Up to a wiggle ratio,
which
is still a bit mysterious to me. So this is about categories which are constructible in your programming language.
Right.
So it says something, it doesn't also imply that the way you prove the equivalence has a bound. Because you can construct equivalences between these categories in many extremely complicated ways.
Right.
But somehow the complication of this equivalence is bound by the nature of the categories themselves. Because let
me tell you what that wiggle it means.
Yeah.
It means you give me an equivalence of categories, and with a finite amount of steps, I will get you this one, and I will get you that one, in some sense. So it doesn't matter how complicated the equivalence is. And by the way, Kolmogorov complexity is always interested in the simplest equivalence of categories.
Well, I don't completely understand your answer, but another way to phrase the same question perhaps is why don't the explicit equivalences, the functors which establish the equivalence, not occur in the study?
Can you give me an example of two categories that are equivalent, but there's no functor equivalence functor in between them? I mean, this has to do with your set theory, with the axiom of choice.
No, I mean, if you look, the complexity of the functors that establish the equivalence can vary quite a lot, right?
Right.
Now, is your tilde depending on will you just say that?
No, it doesn't depend on that. It doesn't depend on how complicated it is.
Right.
In some
So
sense,
so does your theorem also say that if I prove in a very complicated way that constructible, let's call them constructible categories are equivalent, then because of your invariance theorem, there must be a simpler functor?
I think so.
It seems to say something like this, right?
Right. I just want to say, the vast majority of categorical structures cannot be programmed by Sam. Okay? Just like the vast majority of numbers. In other words, take a simple category. Take the natural numbers like this. Take the category of 2, zeros and ones. Okay? So the natural number, now take the functor category from the natural numbers 2, 2. Basically picking out for each natural number, picking out either a 0 or 1. That's equivalent to the real numbers. Okay? So you have, that's the real numbers. Question, how many Sammy programs are there? Countably infinite. How many real numbers are there? Uncountably infinite. So the vast majority of functors from the natural numbers to 2 cannot be constructed. That's a simple case, but obviously most things.
Some other questions or comments?
Just related to the same discussion just now. So I got the impression that you were saying that the precise formulation of this statement regarding equivalences of categories was that there is a constant such that for any equivalence of categories constructible in the system, the difference in Kolmogorov complexity between the two is less than that constant. Is that correct?
Right.
Yeah, so that's sort of a precise formulation.
Can you repeat
There exists a constant. I start off with that. There exists a constant amount of operations, such that if you give me any two categories that are equivalent, or if he gives me any two categories that are equivalent, they'll both be. I'll be able to show this equivalence in less than that constant. Okay, so the constant comes first. You might see it over here. Hold on. Let me just.
If you can compute your complexity of those.
Right. Here, first goes there exists a constant, such that, and then the constant is used. So if yes. And by the way, I have, one paper was published and the other paper I'm in the middle of, but I have copies if you want. It's also available. And I finished on that.
So if there are no more questions, please, I can speak again. We have a break to 10 minutes.